Hi everyone, this is Mr. Lee. In this video, we're going to go over the bowling ball activity and a couple of different notes for how we can create different models for this unit. So this unit is called the free particle unit. Let's begin. So there are a couple of things that you should have taken away from the bowling ball activity. So I'm going to write them down here. So one, the pushing / pulling of objects will accelerate. All right. Now, from there, we can get into a little bit more of a definition of what we can call acceleration. And in this case, acceleration, there's actually three definitions that we'll go over. The first one is either speeding up. The second one is what we consider to be slowing down. And the last one, this one is a new one, and this one is called changing direction. All right. So if you take a look at this, all three of these are represented in a car. The speeding up, this is what we call the gas pedal. Okay. Slowing down, these are called the brakes. And changing the direction, this is what we call the steering wheel. Right. So all three representations of acceleration is represented in your car. And you can accelerate an object by pushing or pulling on the object. And that's important. The idea of pushing and pulling is the focus of this entire unit. All right. Another thing, too, just as a quick reminder, the speeding up and the slowing down, that depends on the velocity of the object. Okay, but this is something from Unit 2 that I'm noticing a lot of students mix up on. Okay, so only velocity tells us the direction of motion. Okay, and that is especially true for this unit. So let's not get that confused. And what I mean by only velocity tells us the direction of motion, we either have a positive velocity or a negative velocity, right? And the positive velocity we say is either up or down, or excuse me, up or right. And left we say either left or down. Okay. Now, the way that a lot of students get this confused is by thinking that the acceleration tells us the direction of motion, right? But that's not the case. So let's write down acceleration does not equal the direction. Okay, it only tells us how much that velocity is changing. So for example, a lot of students believe that if you have a positive acceleration, this does not mean that you're moving to the right. Okay, or if you have a negative acceleration, it does not mean that you're moving to the left. Only if you have a positive velocity, this is when you're moving right or up, or if you have a negative velocity, this means that you're moving left or down. Also, position. Okay, position does not tell us the direction. This is very important. So another way to think about it is if you are in the negative position, okay, this does not mean that you're moving to the left. If you have a positive position, this does not mean you are moving to the right. Now, the way that this is represented a lot of the times is with the three graphs. So let's start off with the velocity time graph. Okay, so here we have a velocity time graph. I'm just going to create a simple line there. Down here in this region, I'm going to highlight this part. This tells us that we have a negative velocity. So this is a negative velocity. So what this shows us down here is that we are moving, I'm going to just say left. But up here, you'll notice that we have a positive velocity. So what this tells us is that we are moving to the right, right? And the way that this graph is represented on a position time graph, it'll look something like this. So down here we have a negative velocity. So as a reminder, the slope of a position time graph equals our velocity. So I'm going to start off by going in the negative direction, okay, like so. And right here, that's where our velocity is 0. So we are going to flatten out a little bit, okay? And then we have a positive velocity, so my slope is going to go upwards, like so. All right, notice here, this entire time, I purposely drew it so that we are only in the positive position portion of the graph, but this does not mean that we are moving to the right, right? So if I were to do the highlighter trick, I would say that this entire portion right there, we are moving left, and this entire portion right here, I would say we are moving to the right, okay? And if you remember from the last unit in class, we spent a good amount of time color coding our worksheets so that this is the correct representation. All right, now let's actually get to this new unit. And this new unit is all about acceleration. So the acceleration time graph. All right, so with the acceleration time graph, as a reminder, from the velocity time, the slope of the acceleration time graph is, the slope of your velocity time graph is your acceleration. So if I take a look at my line here, I see that this is all a positive slope. And some of us might use the word constant, but I want us to be a little bit better than that. Instead of saying a constant slope, I want to say we have a constant positive acceleration. Okay, we have a positive constant acceleration. So that here I can draw it like so. All right. Now, here are the three graphs, and for this unit, our main focus is actually with this one, the whole idea of acceleration. And let's go to the next part. So for this unit, a big important part of this unit is having the ability to create what we call free body diagrams, okay? Diagrams. You might also hear me call it a force body diagram, okay? And it's a diagram that shows us how to draw all of the forces acting on an object. By the way, a force is what we defined earlier, a push or a pull, okay? A force is either a force or a pull that is acting on a single object. So the best way to really do this is to go over a couple of examples, but there's a couple of rules that I want to go over as examples show up. All right. So the first one, let's say we have a book on a table. All right. So we have a book on a table. In order to represent these objects, I just like to represent it as like a box or a dot. Okay, a dot's really helpful if the object is rolling or moving, or you may even see me do both, a box with a dot, right? So any object can be represented as a box or a dot, or a box with a dot. And for this one, I will draw, let's do a box, okay? Because a book looks like kind of like a box, right? It's really up to you. You can do a dot if you want. And the next thing I want to show you is here we have a surface. Now the surface, drawing the surface is very important. It's pretty much key for a lot of parts of the physics units because the surface tells us a lot about what's going to be happening with the object. All right, so for the first two units, one of the things I kept on emphasizing is the verbal, right? The verbalization of the scenario. And that's still very important here. So if we have a book on the table, we can say object or the book is at rest on a table. So now you can see I'm adding to my verbalization here, I'm including this part on a table. And that is because the table or the surface will give us a force. So we'll call this the surface, right? And so the surface force, let's put a definition down here. The surface force is what we call the normal force. Now, the word normal isn't like the everyday use of the word normal, like, oh, the sky is blue. Well, that's normal. Or my car is moving. Oh, that's normal, right? So that's not the type of normal that we're talking about. Normal in this case is a mathematical term, which means 90 degrees or perpendicular, okay? Perpendicular. That's what normal means. And so the force will be normal to the surface. So I'm going to write that down. The force is normal to the surface. So if I have the surface here, I'm going to maybe be a little bit more bigger. So if I have a surface here, the force that the surface is acting on the object will be 90 degrees. So if this is my surface here, I'm going to draw the force away from the surface, like so. I'll do it in a different color. And this is going to be 90 degrees. And I like to put those 90-degree symbols there to help us remind ourselves that this is a normal force. All right. Now what we have to do is we have to label the force. And labeling the force until we get really, really comfortable with all the different forces, I'm going to ask you to label the forces in the following fashion. Right? So let's do that over here. Make it nice and big because it's important. So this is what we call the how to label. All right. So F, and there's a little subscript down here. So subscript is like not with the normal line of text, but slightly below. We can say the object. So force of, agent, comma, on object. All right. So what agent means is that is the thing that is causing the force. And I'll write that down. This is the cause of force. And the object, this is the object in the problem. So this will be either the box or the circle, or right. So the box or the circle or the box circle, right? That is the object itself. And so for this force here, we can write it as F, okay, of the surface. So I'm going to just write the surface as N. Okay, you can write it as S if you want, but remember, we're trying to get used to calling it the appropriate things. So that's a normal force on the book. Okay, so F of N on the book. All right, so the comma just simply tells us that this is on. So I'm going to write that down. This means on. All right, so that's one force then. Now, the other force that is acting on this book that we don't see is from the Earth, okay? And that is what we call a long distance force. But for our class, what you need to know is, say, the force of the Earth, comma, on object, okay? This is what we call the force of gravity. And another way to represent this is weight. So the force of gravity is the same as the weight, okay? And the weight and the force of gravity is caused by the Earth on the object. And for us, it's very important to know that the Earth always pulls down. And here's that important word for this unit. Okay, the Earth always pulls the object down. So for our diagram here, I'll use a different color. Oh, let's use purple. Yeah. Okay. I'm going to draw this line straight down like so. And I'm going to say F of the Earth. You can label it as F of G or F of E. Okay. Comma on the book. Right, so there's a lot of different ways to write that there. I just showed you one of the ways. In fact, on these below here, I'll write the different ways. So you can either call it the F of the Earth, you can call it F of lowercase g for gravity, and eventually when we get used to all this, we'll just label it as W, but let's save that for later. All right, cool. Now, here's the next important thing. The other idea here is the idea of acceleration. Okay, is this object accelerating? Is it speeding up or is it slowing down? And we get that from the verbalization right here. So if the object is at rest, is it speeding up or is it slowing down as time moves on? So think about it. If the book is on the table and 5 seconds later the book is still on the table and hasn't moved, did it speed up or slow down? If your answer is no, what we have here is what we call a free particle model, where we can say the acceleration is 0 meters per second squared. Okay, so what this means is that we will always have a constant velocity. So I'm going to write that there in my verbal as well. So velocity is constant of 0 meters per second. So once again, I'm trying to emphasize here the verbal is so very important because it tells us exactly what to put down. So if our acceleration is 0 meters per second squared, that must mean that even though we have two things pushing and pulling on the object, both of those forces are canceling out. So to show that, this is what we call the symbol for equality or equal forces. I'm going to draw a line here and a line there. Okay, so you might remember this from your geometry class or your first trig class, but that's just to show you that those two values for the forces or the magnitude of the forces are equal to each other. Okay, now if you have more forces drawn on there and you have more forces that are equal to each other, we would just increase the number of lines to show us that it is equal. Okay, but a good way to do it is to just draw them as if they were equal. All right, so let's do another scenario. Okay, let's do 2. So let's say we have here book is pushed to the right. So this is my verbal, right? Book is pushed to the right and it's moving with constant positive velocity. Okay, so if we're moving with constant positive velocity, this means that your acceleration is 0 meters per second squared. And I'm going to put a little clue there. There's a rough surface. Now, what that rough surface means is that there is a force of friction. Okay, so keep an eye out for those keywords. All right, so let's draw it. I'm going to represent the surface there, right? Very important. We have the book on the surface, right? The very first force I'm going to draw is the force of gravity on the object. So I'm going to go straight down. Let's call this F of E on the book. Okay. And we also have a force going up. So I'm going to keep it the same color because these two forces are equal to each other. So here we have F of the surface or the normal force on the book. Okay. And we're pushing it to the right. So here's a new force. Let's use a different color green. All right. So we are pushing the book to the right. So notice all of my my force vectors are always going away from the object, right? So it starts from within and then it moves away. You never want your vectors to go into the object. So for this one, we can call it just f of 1, right? Because there's no like special term for a push or a pull, like that is a force, right? So a push or a pull is a force. So I'm just going to give it a number. So I'm going to call this F1 on the book. Okay, and the next one, we have a rough surface, so we call that the force of friction. And I'm going to draw that. Let's do a different color. This is a new one. I'm going to draw that to the left. Okay, we're going to call that force of friction on the book. All right, so here we have our 4 forces. It's important to identify which forces are equal. So at this point, it's important to identify the x and the y axes. So this is my y-axis, and this is my x-axis. A better way to really call this is my vertical axis, and this is my horizontal. You'll hear me call it both ways, but just so you know. So we know that the vertical forces, okay, they're equal. And if I were to ask you, why are these forces equal? We can say the Fn on the book is equal to Fe on the book because the acceleration is equal to 0 meters per second squared, right? We're not speeding up or slowing down in the vertical axis. So in the vertical axis. All right, and we can also say F1 on the book is equal to the force of friction on the book. And that's because the acceleration is equal to 0 meters per second squared in the horizontal axis. Okay? So now we have all of our evidence to make this claim true. So to show that these two forces are equal, right, we already use one line there, so we're going to call this the double lines, right, to show that these two are linked. Now we can see that they're linked visually, but once we get into the more complex things, having these rules in place really does help, right? Okay, so now you might be wondering, but Mr. Lee, how do we show that this object is moving? Well, if you remember, this diagram is all about forces, and forces, they push and they pull, okay? And if you push or you pull, that means we either speed up, we either slow down, okay, or the new one, we either change direction, okay, and speed up, slow down, or change direction. This is all about acceleration, right? And acceleration does not equal velocity. And velocity is the only thing that tells you how it's moving. So we don't actually, on the object itself, we don't say the velocity, right? That always comes from the verbal. But if it makes it feel you, if it helps you out, makes you feel better, what I like to do is right like in the corner somewhere, I just like to say velocity is positive, okay, with no arrows. So it's important to know that the only arrows that you draw on a free body diagram are from the forces, and the forces are simply there to show you how it will accelerate. Okay, no velocity arrows at all. You can label it in the corner there as a reminder that it is moving to the right, but no velocity vectors. Okay, wonderful. So we have that. We went over the force of friction. We went over the force of gravity, or the force of the earth. We also went over the normal force, or the surface force. And the only other force that I have to really show you is what we call the force of the spring. And in class, we'll be dealing a lot of with springs, and so it's important to know how to draw these diagrams. We can say an object is held up by a spring. Okay, and we can say the object is motionless, and your acceleration is 0 meters per second squared. All right. So what I'm going to show you is a little bit of flare if you want. So for the free body diagram, no flares involved, but the important part of physics is actually being able to sketch what you see and labeling the sketch. And so I'm gonna do a quick little sketch here. So we have a spring and we have an object, right? And to show that it's not on the floor, I'm going to draw the floor way below it. Okay, so it is held in the air by a spring. All right, so that's my diagram. You can label it whatever you want, but here's my free body diagram. So I have my object there, I have my surface way down there, okay, just so that there's no temptation to draw the normal force. The very first force I'm going to draw is the force of gravity acting on the object. Okay, so we can say this is F of G on the object, so I'm just going to call it on the block. Okay, and what's the spring doing here? Right, we see that the spring is holding this object up. Now here's something cool about springs. Springs always do the opposite of what you do to it. So if you push on a spring, the spring pushes back. If you pull on the spring pulls back. And so what we can think about is that this block is pulling on the spring downwards. So the spring is holding the block upwards. So we can label this as F of spring, or F of S if you want, on the block. Cool. And that's that. The only thing I have to draw are my equal lines, or equality lines, to show that those two forces are equal to each other. Alrighty? Wonderful. The only other thing that we can do is like a combination of all of them, but that'll be for a different day. Anyways, and that was Mr. Lee, and this is how you draw free body diagrams. See you later. Bye-bye.